have a monoatomic ideal gas, and it goes through a series of four steps, beginning with a free expansion into vacuum. And we'll talk about that in a little bit. And after that free expansion that triples the volume, then it is heated reversibly at constant volume. It is reversibly expanded at constant temperature to triple the volume, and it's finally reversibly cooled. And for each one of these transitions, we're supposed to calculate the heat and work, or heat transferred and work done, and then the state equations, state variables. So let me zoom out here. We'll start just by writing down the initial conditions. We have 1 mole, 300 K, pressure is 10 atmospheres, 10 ATM, and then the volume is nRT over P is equal to 1 times 8.2 times 10 to the minus 2 times 300 over 10 is equal to 2.46 meters. And then this undergoes a free expansion. So this free expansion is basically a situation in which we're saying that it triples its volume. We're saying that the system here, all the gas is on one side, and then abruptly we remove this wall. And when we abruptly remove that wall, the gas rapidly expands into the volume that was previously vacuum. By free expansion of an ideal gas, we're actually specifying a set of behaviors. In particular, this free expansion is not doing work on the environment because it's just expanding within its own system. So no work is done. No temperature changes because the gas is ideal and it's not absorbing energy from the environment in the process of removing that wall. And real gases, of course, there is a change, but for an ideal gas, this isn't the case. And because delta T is 0, and because delta T is 0, delta U is 0 as well. And if W and delta U is 0, then Q is also 0. And delta H is equal to 0. So basically we have this change, and this is just purely a change in the entropy. So let's, I shall also specify in this problem that CV is equal to 3/2 R. So we still have 1 mole of gas. We have same temperature. We have a volume now, which is different. The volume is now 3 times, so that's going to be 7.38 liter. And now P is equal to nRT over V is equal to 8.2 times 10 to the minus 2 times 300 over 7.38 is equal to 3.3 atm. So we have a new pressure. So in the previous problem, we wrote out our entropy expression. This ds is equal to ncv over t dt plus nr over v dv. So we can use this, and here at 0, because temperature isn't changing, it means that delta S equals nr ln v2 over v1 is equal to 1 times 8.314 times natural log of 7.38 divided by 2.46. Our delta S is equal to 9.13 joule per K. So we've got our solution for that first step. And we'll go to the next. The next is a gas heated to 400 K at constant volume. So constant volume, N3 is equal to 1 mole. T3 is now 400. That was specified in the problem. V3 is constant, 7.38, which means P3 is equal to nRT over V is equal to 8.2 times 10 to the minus 2, 400 divided by 7.38 is equal to 4.4 atm. Okay, so we got a new pressure. So it's a constant volume problem, which means that W is equal to P delta V 0. So W is equal to 0. And now delta U is equal to Q minus W 0. So delta U is equal to Q. And that is equal to NCV delta T, right? Because we know that we can relate change in internal energy to change in temperature by the heat capacity. Which is equal to 3/2 times 8.314, the gas constant, times 100, that's delta T. So we have delta U is equal to Q is equal to 1, 2, 0.47 joule. Okay, and now we've got delta H is equal to delta U plus delta PV is equal to 1247 plus 4.4 times 7.38 minus 3.3 times 7.38 times 101 joule per atmosphere liter. So delta H is equal to 2067 joule. And going back and using our expression for the entropy, holding V constant and recognizing that delta T changes, we can write delta S is equal to N CV natural log T2 over T1 is equal to 3 halves 8.314, the gas constant, natural log of 400 divided by 300, delta S is equal to 3.59 joule per K. Which gives us the last part of the second step. The third step now. The third step is what? Third step is a reversible expansion at constant temperature to triple the volume. So constant temperature, and 4 equals 1 mole, T4 equals 400 because it doesn't change, P4, V4 now triples, and tripling that makes it 22.14 liter, and P is equal to nRT over V is equal to 8.2 times 10 to the minus 2 times 400 divided by 22.14 is equal to 1.48 ATM. Okay, so we have the new state. So for a constant isothermal expansion, delta T equals 0 means that delta U equals delta H equals 0. And delta GU equals 0 means that Q equals W is equal to N RT natural log V2 over V1, or I guess in this case V4 over V3, is equal to 8.314, the gas constant, times 1 is 1 mole, times 400 natural log of 22.14 divided by 7.3 438. The original state. So Q equals W is equal to 3654 joule. And now the entropy, delta S, is equal to, again going back to our original expression here, delta T is constant, we get this. Delta S is equal to NR natural log V, 4 over V3, let's call that 4, 3. Is equal to 8.314 natural log of 22.14 divided by 7.38. Delta S is equal to 9.13. That's joule per K. Okay. Now the next step is a constant pressure. And the constant pressure is a constant pressure cooling the gas to 300 K. So cooling the gas to 300 K means that N5 equals 1, T5 equals 300 K, P5 equals V5 equals constant pressure, so V5 is still equal to 1.48 atm, which means that now V5 is equal to nRT over P is equal to 8.2 times 10 to the minus 2 times 300 divided by 1.48 is equal to 16.6 liters. Okay, so we've got the state. This constant pressure change. We have W is equal to P delta V is equal to 1.48 times 16.6 minus 22.14 times 101 joule per atmosphere liter. W is equal to minus 828 joule. Q, P is equal to delta H. Remember this from chapter 2. Is equal to N Cp delta T is equal to 1 times 5 halves of the gas constant, 8.314 times 300 minus 400. Q equals delta H is equal to negative 2079 joule. Delta U is equal to Q minus W. We've got both of those. So we get minus 2079 minus negative 828. Delta U is equal to minus 1251 joule. And lastly, we have delta S is equal to N CV natural log T5 over T4 plus N R natural log V5 over V4. And again, this is coming from our original expression for the derivative of the differential of entropy. And that is going to be equal to 3/2 8.314 natural log 300 over 400 plus 8.314 natural log of 16.6 divided by 22.14. Delta S is equal to minus 5.98 joule per K. So that gives us all the parts we need. And lastly, we kind of put it all together. Page 16, we get Q is equal to 1247 plus 3654 minus 2079 is equal to 2822 joule. Work is equal to 3654 minus 828 is equal to 2826 joule. We have delta U is equal to 1247 minus 1254 is equal to minus 4 joule. Delta H is equal to 2067 minus 2079 is equal to, what is that, 3 and 9. So minus 12 joule, and delta S is equal to 9.13 plus 3.59 plus 9.13 minus 5.98 is equal to 15.9 joule per K. And these two, we put these two together, right? We get minus 4 joule. So it's properly behaved. My assumption is that the way that the problem was designed, if we carried this out to a higher number of decimal places, this would go down to give us a 0U, but we rounded at basically the units of ones, so it's okay.